So what do we have to do so that we can actually turn this formula into a coupled ordinary differential equation we can solve?
Approximate the derivative as a finite difference.
Approximate the derivative as finite. We only have a time derivative here, right? I mean, it's when we basically the goal of the spatial discretization is to get rid of the spatial derivative and turn this into an ordinary differential equation. So what I'm asking is that it seems that we already achieved that, right? I mean, there is no spatial derivatives here at all. So why can't we just plug this equation into an ODE solver and solve it? What step are we missing here? What prevents us from turning this into a coupled ODE? Let me ask in another way. So if we turn this into an ordinary differential equation, what would be the variables? What would be the vector? What would be the unknowns? Well, the unknowns are actually these averages, right? So that's like what finite volume method is doing. Remember, in finite difference, the unknowns are the values of the functions at the grid points. In finite volume, this graph is what I'm trying to show you, is that the unknowns are no longer the values of the function at the grid points. It is now the average of the function within the intervals. So if I use finite volume, the unknowns will be u bar from 0 to delta x, okay, u bar from delta x to 2 delta x, etc. Right? This is going to be unknowns. And so this would be my vector u, the vector of unknowns in my ordinary differential equation. So I have to write down du dt, which is the time derivative of these time averages, as what? In order for me to be able to solve this ODE. As a function of these averages, right? As a certain function of this u, right? So the question is, how can I write the difference in fluxes as a function of the volume averages? So that's actually the tricky part about finite volume. The tricky part about finite volume is that we actually, in contrary to finite difference, where we know the value of u exactly on the domain interfaces, right? This is like a finite difference. This is finite volume. But in finite volume, we no longer keep track of the value of u at the interfaces, right? We only know the averages over the volumes. So in order for us to be able to write the right-hand side as a function of the time averages, we have to approximate the point-wise value of u by using the left and right volume averages. Does it make sense? Yeah, the only, so there are, like finite difference, right? Finite difference, we have different schemes. We studied the left biased scheme, a right biased scheme, and the central scheme. There are different finite different schemes. There are also different finite volume schemes, and the only difference is that how do you approximate the fluxes, the flux at the interfaces, using only the volume averages of u. Okay, so the key about finite difference, about finite volume, is to how do I approximate f of u at a certain interface, let's say I times delta x, How can I approximate it as a certain function? Let me write as f tilde, signifying it is an approximation. Approximate it as a function of u bar, the average between I minus 1 delta x and I delta x. So that's the left of this interface. And u bar, again, on the right side of the interface, averaging starting from I delta x to I plus 1 delta x. Okay, so if we know how to approximate this, as an example, I can approximate this if I just take f of, for example, because I usually know what f is, right? As an example, I just take the average of u bar left plus u bar right, right? So let me just say, I just shorten this as u bar left and shorten this as u bar right. Okay, then this is an example approximation of the flux, and then we can solve the equations, right? Any questions on what I did and why do I have to do this?
So is the f in that equation you just wrote, is that the flux or is that the derivative approximation?
The f is our flux, right? There is no approximation in finite volume until we get to this point. This is where approximation started. And f of u is actually exactly the flux function. And for burgers, we know f of u is u squared over 2.
So are these functions the same for finite volume? Or is f tilde, is that a different function?
F and f tilde are different functions. So f tilde is an approximation of f of u because I actually don't have the exact value of u. So I have to approximate the flux using the left average and right average. So f tilde is actually a bivariate function. F is a univariate function. F only depends on the u at the interface, but I don't have u at the interface. So that's why I approximated using f tilde, which is a function of the average at the left and right of the interface. Right? So f of tilde depends on the averages on the two sides of the interface, where f depends on the exact value on the interface. Make sense?